Okay, so last time we were talking about capacitors. Okay, we have two types of circuits that we can do with it. Well, we have capacitors and inductors. Last time we talked about capacitors. We can have a capacitor in series with a resistor, and it will be connected to a voltage supply. This is known as an RC because this is your capacitor, this is your resistor, and this is your voltage. This is known as an RC circuit. Another type of circuit that we didn't talk about last time is an LR or an RL circuit, where you have an inductor, a voltage supply, and a resistor. So you have your resistor, this is the symbol for an inductor, and this is your RL circuit, and this is the voltage supplied by by the supply. So a few notes you should know about this is when you have a voltage supply, this is basically charging in both cases. So here you're charging the capacitor, and here you're charging your inductor. All right, the L. Okay, so when you charge the inductor, معناتها it is going to be fully charged and it can act as a temporary battery, the same idea as a capacitor, but the component works in a slightly different manner. That's the only difference over here. When we're looking at capacitors, all right, we're going to be using a specific set of equation for an RC circuit. And when we are looking at an inductor, we're going to be using a specific formula as well, but they're very similar in application. So what happens is the charging occurs in milliseconds usually. And once this is fully charged, this is the charging, basically, when you have a voltage supply attached to them. And if you are discharging, this is what it will look like. So you're going to have only your capacitor and, for example, a resistor. Okay, this is C and this is your R. This is known as discharging. معناته whatever is charged that was stored in your capacitor, now you're letting it out throughout the circuit. So this is the discharging for the capacitor. The same idea for an inductor. Okay, so this is your inductor and resistor. You're going to have a discharging as well. And in this case, you're discharging, your values will change or your equations will change. Let's take a very quick look at the equations for a capacitor one more time. In the case of charging for a capacitor, this is the values that you're going to be, or the equations that you're going to be using, and I'll explain them in a bit. And in case of discharging, you're going to be using the decay voltage. So one thing you guys need to notice here is, excuse me, here your VC is different than your VR, but in the discharging, your VC is going to be the same as VR, and the decay of current is going to be the same throughout the circuit. Why is this the case? لأن هني خلاص they're connected in parallel directly to each other. معناته the voltage is going to be the same for both. Here the voltage is different. The voltage of the capacitor is different than the voltage of the resistor. Remember that the voltage for a capacitor is equal to the charge. This is VC over R. Over capacitance, and here it is VC is equal to IR. All right, in this case over here, VR and VC are equal to each other, and you will be using this equation, which is the decay of voltage for both. Let us just dive into a question for a capacitor so you guys know what I am talking about. Let's start with this one. So here it says you have a 10 microfarad capacitor that is connected in series with a 90 kilo ohm resistor. So the first thing you're going to do here, remember your units. So you have C equal 10 microfarads, معناته 10 times 10 to the minus 6 farads. Same thing with the resistor, your R is equal to 90 kilo ohms, or in other words, it's 90 times 10 to the power of 3 ohms, or 90,000 ohms. All right, so make sure you are converting to the right units, and they are connected to a DC supply of voltage 20 volts. All right, so you basically have a charging of the capacitor in this case because they're connected to a DC supply. Part A says determine the time constant. Remember, your time constant is simply just R times C. In the case of a capacitor or an RC circuit, it's just the resistor times the capacitance. So you're just going to be multiplying the values with each other, which is very straightforward. So 10 to the power minus 6, 10 times 10 to the power minus 6 times 90 times 10 to the power of 3. 10 times 10 to the power of minus 6 times 90 times 10 to the power of 3. you're going to get 0.9 seconds. So this is your time constant. All right. Remember, your time constant is just a property of the circuit that shows how fast or how slow the charging rate is. So this is for part A. Part B, the initial value of the current flowing. What do they mean when they say initial value? So initial value basically means you are finding your maximum current. All right. Because initially in a circuit, if we draw the circuit over here, what they mean when they say initially is basically you have a switch over here. And as soon as you close the switch, technically the voltage here is still zero. The voltage of the capacitor is still equal to zero. All right. So the voltage of the resistor is going to be equal to the voltage of the V total, the voltage source over here. So how can you find the current that is going through? It is simply equal to V over R. If you remember, V is equal to IR in the case of the resistor. So it's only the resistor that will be in effect when it is initial value of the current flowing, meaning that it is at the very beginning of when of when you have the circuit closed. So what does that mean? That simply means that you're just gonna multiply or find your V over R, which is your voltage is given in the question to be 20, and you will divide by the resistance value that was given, which is 90 times 10 to the power of 3. All right. And this will be your I max or your I initial. Again, the reason it is just I over or V over R is because the capacitor is still not yet charged. There is no voltage when it is initially connected or when the switch is initially closed. That's why you're only going to be looking at the resistor value. So it's going to be 2.22 times 10 to the minus 4 amperes. And in milliamperes, this would be it's going to be 22.2. It's going to be 0.22 milliamperes. All right, you can use the trick that I said in the calculator, convert this into 10 minus 3, and you will see that it's 0.22. Okay. The value of the current 2.8 seconds after the connection. So here you're just going to be using this equation over here. All right, for part C. Now remember, when you are looking at a charging of a capacitor, معناته you have a voltage source connected, you'll be using these equations to just determine all the values that they ask for. So the value of the current 2.8 seconds after the connection, you're going to be using the equation of current. So I is going to be equal to large I. This large I is basically I max, all right? This large I over here, this is your I max, e to the power of minus t over tau, which is your time constant. Okay, and that's it. And then you're just going to plug in values. This is equal to 0. Or actually, you have to keep it in. Technically, you don't. If you're finding current, you can keep it in milliamperes in the equation because you're finding current, and current will also be in milliamperes. So you don't necessarily have to do your conversion here, but make sure you know that your final answer is going to be in milliamperes. All right. So it's going to be e to the power of minus t. If this is too confusing, just convert it back into amperes and find your final answer in amperes. I recommend usually you do this if this is too confusing. So e to the power of minus t. What was the time given? Our time is 2.8 seconds after the connection. معناتها our t is equal to 2.8 seconds. All right. It's not milliseconds, it's seconds. So we can directly plug it in as 2.8 over tau, which is the value that we have already calculated of 0.9. So this is going to be equal to alpha e power minus 2.8 divided by 0.9. You will get a value of 9.9 times 10 to the negative 3 milliamps. All right, so it is a very small value, which makes sense because current will be going down and down the more time that is flowing because the capacitor is almost fully charged. Okay, this is what you're going to do. انزين شوي بحاول أبطأ. Okay, so again, I'm just going to do a quick recap at the very beginning. Tau is equal to RC. This is just your time constant from the equation. Make sure your units are correct. Part B, we are talking about initial value of the current flowing, which is I max. Okay, I max is simply just the current that is initially flowing in the circuit when there is no voltage or no charging that is happening in your capacitor. When you have no charging happening in the capacitor, remember that your V total is equal to VC plus VR. All right. Since the capacitor is zero, معناتها our V total is simply equal to the voltage across the resistor, which is equal to I times R. All right. And this value of I is your I max. معناتها we are doing I max is equal to V total over R, and that is what we have applied here. So the V total is the voltage supplied by the battery or by the source divided by the resistance that you have in your circuit. This is always going to be your initial value of the current, or in other words, your maximum current in the circuit in the case of an RC circuit. تمام? After that, part C, they asked for the current or the value of current 2.8 seconds after the connection. معناتها you have already done this connection, you have closed the switch over here, 2.8 seconds has passed by, and now you want to find the current in the circuit. During this time, the current is going to be following this equation, all right, which is IE minus T over tau, where your I is basically your maximum I, all right, your maximum value of I, which we have found in part B, okay? Once you find, excuse me. Okay, so once you find your Imax, you can use it in this equation, all right? Even if you don't find your Imax and they ask for this directly, you can always find your Imax by just closing or by just equating your VC to be 0 and just doing V over R, you know, simple Ohm's law. Once you find your Imax, you can use it to find at any point of time the current during the charging process using this equation. So they gave us a specific time of 2.8 seconds after. So this is going to be our T value. All right. And our tau we found from the beginning, and you can always find depending on your resistor and your capacitor. Now, let's look at part D, the value of the capacitor voltage 3.8 seconds after. So what are we looking at now? We have a new time of 3.8 seconds. So now T equal 3.8 seconds, and we want our capacitor voltage. What from this equation over here, growth of capacitor voltage is here, all right? So this is the equation that you will be using, V1 minus E minus T over tau. So for part D, V capacitor is going to be equal to V, which is simply your V total, all right? The V of the voltage source. And this is what V is, into 1 minus e to the power of minus t over tau, and you just plug in your values. So V total is given to us in the question to be 20 volts. So 20, 1 minus e to the power of minus t. The time that we had given was 3.8. So minus 3.8 divided by tau, which is the value that we have calculated early on as 0.9. Plug this all into your calculator, you will get that VC is equal to 20 into 1 minus e to the power of minus 3.8 divided by 0.9, which is 19.71 volts. Okay, and this is the value of your capacitor after that specific time. Keep in mind, the value of the capacitor can never go over the value of your initial voltage. لأن خلاص, when it is fully charged, معناتها it has already, it is going to reach the voltage of your source, which is 20 volts. If you get a number that is larger than that, know that you have most probably done a mistake in your calculations. Okay, very simple. You just have to plug into equations. Here it says the time after the connection when the resistor voltage is 15. So now they're talking about the resistor voltage. They gave you R or VR to be 15 volts. All right. So this is your last equation over here, which is your decay of the resistor voltage, which is VR. You will be using this equation, which is for part C or part E, VR is equal to VE minus T over tau. All right. So I'm just using this equation over here. Now, in this case, we were not given our time. This is what we need to find. Best, we know what this V is. This is, remember, just V total, the source V. So, and we were given that VR is equal to 15 volts. All right. So VR in the question was given to be 15 volts. We know that 15 is equal to VT, which is 20 volts, e to the power of minus t over, for now, I'll keep it as tau so that you don't get too confused, but it's minus t over tau. All right. We take the 20 to the other side. You're going to have 15 over 20 is equal to e minus t over tau. So when you have this case, okay, when you have this case, how do you solve for an exponential? All you have to do is you're going to be applying for both sides ln. Right? So you're going to be applying ln to both sides. When you have an exponential, this is how you solve for an exponential. You're just going to be applying ln to both sides. What does applying ln to both sides mean? This basically will, so this is just a value, a constant. So on the left side, we're just going to have ln of 15 over 20, which is just 3 over 4, okay, is equal to the ln of E is simply just, they cancel out each other and your power is going to be the answer. So minus t over tau is going to be your answer. All right. This is the power of ln. This is what ln does. It cancels out the exponent and whatever the exponential function has the power and its power basically في الأس ينزلونه تحت and it will become part of your equation. This is how you use your ln function. All right. This is just general mathematics, how the application of the ln function. So by the way, you can apply ln, you can apply log, you can apply whatever you want, right? It doesn't matter. But ln is what is mostly used when you are dealing with E, okay? So, yeah, and that's it. And now this is a value that you can find from your calculator. So ln of 3 over 4 times tau is equal to minus t. Remember, tau is simply just 0.9 that we have calculated early on. معناته our time is going to be equal to 0.9. أحس مسوي شيء غلط. Let me just double check my work. This is minus t, okay. 15 over 20. And then, okay. No, it looks correct. So it's going to be negative 0.9 ln of 3 over 4. So t is equal to 0.9 times ln of 3 over 4, which is going to be minus times minus, so 0.259 seconds. Okay, remember in ln, when you have a number between 0 and 1, يعني a decimal, all right, 0 point something, that means the value of ln is going to be a negative number. This is why the negative is here as well, because you can never have time to be negative, so the negative will cancel out with the negative inside of your ln. Is this clear? Clear so far? Can I move on? Okay. So let's look at the same example. However, let's look at when we have discharging. زين. So when we have discharging, معناته now we are using a different equation. So here it says a capacitor is charged to 90 volts and then discharged through a resistor. معناته now our VC, or not our VC, our circuit is going to look like this. Okay, so you have your capacitor and you have your resistor. You are not given the capacitor value, but you are given the resistor to be 25,000 ohms or 25 kilo ohms. If the time constant of the circuit is tau is equal to 0.8 seconds. معناته خلاص, as soon as you have tau and one of the components, you know you can find the other component. In this case, they want the capacitor value. So remember, tau is equal to RC. معناته C is equal to tau over R. معناته C is equal to tau, which is 0.8 divided by 25,000, which is going to be equal to 3.2 times 10 to the minus 5 farads. All right. If you want to find this in microfarads, C is going to be equal to, you use your inch and you're going to see it is 32 times 10 minus 6 or microfarads. Okay. This is for part A. Part B says find the time for the capacitor voltage to fall to 18 volts. Okay, so we want the time of when the capacitor voltage is going to be falling to 18 volts. معناته شو? First, we need to use this equation. وينه؟ هني. All right, now we are talking about decay of voltage. معناته the capacitor has an initial voltage of 90, but it will keep falling down until it is fully discharged and it will become 0. All right, so the voltage is decaying. And remember, since these two are connected in parallel, their voltages are equal. So we're going to be using this equation for part B. VC is equal to VE minus T over tau, where V is your initial voltage, the charged voltage, yani the V total. All right, so it is equal to, in this case, was it 90 volts? It's this value, the fully charged capacitor. All right, so it is 90 volts. So VC, so what was the question? Find the time for the capacitor voltage to fall to 18 volts. So our VC is equal to 18 volts. معناته 18 is equal to 90 e to the power of minus t over tau. What is our tau value? It is 0.8. Okay. Again, same application as before. We are going to apply ln on both sides. Ln of e power minus t over 0.8. Why does ln cancel e here? If you guys remember the rules of ln, and then if we're just looking on the right side now, when you have a power for ln, so if you had ln of x power 5, this is equal to 5 ln x, because you can take the power outside and multiply it. Okay, so this will become minus t over 0.8 times ln of e. And what is the ln of e? The ln of e is simply equal to 1. Okay, so this is why yani this value is equal to 1. This is why you simply just cancel out the ln and the e. This is the actual proof of it. And now you're applying the rule of logarithmics, where when you have a power for any value inside, you can take the power outside and multiply it. This is why we get this value as our final answer. So this is going to be the ln of 18 over 90. So this will cancel out. We will have 0.8, or you could say minus 0.8 ln 18 over 90 is equal to t. معناته our t value, the time it takes for the discharge to reach 18 volts, is ln 18 over 90 times minus 0.8, which is 1.288 seconds. All right, pretty straightforward, pretty clear. The only difference now is the decay equation is being used instead of the charging equation because it is discharging. And if you notice, the discharging equation is the same as the decay for the resistor in the previous equation. It's the same equation exactly. All right, يعني ما في فرق بينهم. لأن here it is charging. So when you have charging, this will always be your equation. When you have discharging, this will always be your equation in the case of an RC circuit. All right. طبعا this is the decay of voltage. If they were asking for current, then you can find the current, which is part C, the current flowing when the capacitor has been discharging for 0.4 seconds. So they gave you time. Again, you just apply the equation. I, or small I should say, is equal to I max e to the power of minus t over tau. All right, this is just your equation over here. What is I max in this case? Again, what did I say I max is? I max is always going to be your voltage over the resistor. In this case, what is our voltage? It is 90 volts. يعني فكروا فيها as the initial voltage, the very beginning, the start voltage, which is 90 volts. لأن as this is discharging, voltage is eventually going to reach 0. معناته there will be no current in your circuit anymore. So the maximum voltage is going to be when the capacitor is just connected, يعني when it is fully charged. So I max is V over R. We can just plug that directly in the equation here. It's V over R E minus T over tau, and we were given the time to be equal to 0.4 seconds from the equation. All right, and then we just solve. Where did the negative go in earlier? Again, when you do the ln of a decimal number, 18 over 90, this is a number smaller than 1. The answer of this ln is going to be a negative number, all right? Just so you guys can see this. This will become minus 0.8 times, if you do ln 18 divided by 90, you're going to get minus 1.609. And here, your negative values will cancel. You're multiplying negative with negative. All right, this is why the negatives are going to be canceling. Now, back to this. T is equal to 0.4 seconds. Now we just plug it into our equation. So I is going to be V, which was 90 volts, over our resistance, which was 25,000 ohms. The exponential of minus t, so minus 0.4 over tau. Tau was given to be 0.8, yes, 0.8. And you just plug into the calculator. So 90 divided by 2500 times your exponential of minus 0.4 divided by 0.8, which is going to be 2.18 times 10 negative 3 amperes, or in other words, 2.18 milliamperes. The whole question is just plugging into the equation. It's just knowing what values to plug. So you just need to understand what the values over here is. You need to know that VC equal VR. This is the voltage of the capacitor or the resistor during discharging. The V, the big V, is your initial value of your voltage, the high maximum voltage. You can think of it that way. And then your minus t, it's just the time that has passed by. And then tau, which is your time constant, which is usually given, or you can find by multiplying R with C. The same thing here, where I is just the maximum current. And then you just plug into this equation for anything. And another other thing you need to know is if you're discharging, you'll be using these equations. And if you're charging, the only equation that will change is your VC will be the gaining equation or the growth equation, which is 1 minus the decaying equation. That's it. All right. So let's look at the last part. The voltage drop across the resistor when the capacitor has been discharging for 1 second. What does this mean? This means we need to find VR. And what is discharging? What is the time? 1 second. Same exact equation again. So part D, VR, which is the same as VC, which is equal to VE minus T over tau, which is going to be equal to 90 e to the power minus 1 over tau, which is 0.8. Plug this into the calculator and you will get your voltage after 1 second across the resistor, which is 90 e power minus 1 divided by 0.8, and you get 25.79 volts. Any questions about this? Is this concept clear for RC circuit? Because RL is almost exactly the same, except a few equations will be different. That's it. But the solving method is almost exactly the same. All right. Is there any questions about RC circuits? Can we move on from RC circuits? When discharging, yes. When discharging, VC equal VR. All right. When discharging, معناته عندكم capacitor with just a resistor. You do not have a voltage source because they're connected in parallel, no? So their voltages are going to be the same. Parallel connection. So their voltages are going to be the same. Okay. So VC is the same as VR only in when you are discharging your capacitor. Moving on to inductors. So we looked at capacitors and how they work. We didn't talk too much about inductors. I'm going to talk about them very briefly now. An inductor is similar to a capacitor in form. يعني when it comes to functionality, the idea of it is to store as well voltage, but the way it does it is using fields. All right, more specifically magnetic or electromagnetic fields. Okay, that's how they do it. How is it done? Because this concept is important. Let's say you have a magnet over here and a magnet over here. If you wrap it around in coils, all right, or not even a magnet, you just have a piece of metal inside and you wrap it around in coils, okay? when you wrap it around in coils and then you run current through this, all right? When you run current through this, in physics, basically what happens is this creates an electrical field. And because you have a metal piece in between them, or a solenoid, also known as a solenoid, you're going to have a magnetic or an electromagnetic field where it will be able to store some energy in this field. So in the capacitor, it was storing it in the plate as electrons. Here, you're storing it in fields. That is the difference between an inductor and the capacitor. And we will look a lot more. We will look more on inductance after we finish with RL circuits. But when it comes to RL circuits, all you need to know is the same idea or the same concepts that we have done are going to be applied again. Okay, so when you have an RL circuit, you're going to have an inductor connected to a resistor, connected to a voltage source. Okay, this is when you are charging, all right? When you are charging. And when you are charging, you're going to have these set of equations to be used. This one. So during charging, this is the set of equations. One thing you need to notice here is your tau is now equal to L divided by R. Okay, it's no longer multiplication now, it is division. All right, that is the main difference over here. But what you notice is during charging, your VL is equal to VE power minus T over tau. Now it is the opposite. So when it is charging, the value of your inductor is doing the opposite. So the way this charges and discharges is basically the opposite of how a capacitor charges and discharges. You don't need to know too much about the theory of that for now, but the idea is the more time that passes by, the less charged this will this will be decaying instead of growing, and the voltage of this will be growing. So here we have V of L, and this is V of the R. All right. So with time passing, the VL is going to be getting less and less. It starts actually with the voltage equal to V and your resistor voltage being at a minimum. And over time, your resistor voltage is going to be high and your VL is almost going to be zero. All right. No need to go too much into theory about that. All you need to know is these are the equations you will be applying. And in the case of discharging, معناته we have our inductor with our resistor in parallel. All right, you're just going to be using the similar equation that we have used before. Exact same equation of decay, which is VL is going to be equal to VR. All right, VL is equal to VR, which is equal to VE minus RT over L, or in other words, tau. And the current, it's the same as well. Remember, the reason they're equal is because they're in parallel. So the voltage discharge is going to be the same. All right, so this is your L and this is your R. All right, inductors are given as the letter L. This is the actual letter they use for inductors. Don't ask me why. I mean, they wouldn't use I because I is used for current, but again, I'm not sure where the L came from, but the unit of an inductor is usually in henries. All right, the unit. This is the unit. So let's say 5 Henry. All right, or simply 5H. This is the unit of inductor. Again, inductors are usually in the milli range, so it's going to be 5 millihenry or sometimes even the micro range most of the time. Okay. That's pretty much it for inductors. Let's actually start solving some questions. This one is too easy. I don't want to start with an easy question. I want to go just directly into it. Actually, let's do this one because there's a concept here I want you guys to understand as well. So, a coil of inductance 0.03. So our L is equal to 0.03 Henry. All right, Henry is the standard unit, and you will keep it in that way. And a resistance of 6 ohms is connected to a voltage supply of 115 volts. Okay. Find the value of the current Imax. Remember, Imax, the same exact concept is being applied in that we did in RC. Imax is going to be equal to the total voltage over your resistor. This is always going to be your Imax. So in this case, it is going to be 115 over 6, which is equal to 19.17 amps. All right, that's a large current. Okay, so again, to find your I max or your I initial or anything along those lines, actually, in the case of inductor circuit, this is going to be your I final, because your initial voltage across the resistor is 0. So your maximum current is your I final in the case of an RL circuit. All right. And because if we want to draw the graph, just so you guys know, of current, initially this is time and this is current. All right. Initially time is 0. As time goes by, at the very beginning, there is no current flowing through the resistor at all. So it is at 0 because of the inductor. The inductor is stopping the current as it is charging. So when it goes fully here, then it stops. This is when it reaches the steady state, if you remember from last class. All right, so this will be your I max. And what did I say? At over a long time, what will happen? Your voltage across L is going to be 0 and your voltage across R is going to be full. So this is equal to VR over R, or in other words, V over R. And this is your I max. All right, this is your maximum current. This is why we apply this equation. Okay, the time constant of the circuit, B time constant, it is not L times R, it is L divided by R. All right, just remember that for an inducting circuit. I'm not sure if this equation is given to you guys. So for a time constant, it's L divided by R, so it's simply 0.03 over 6, which is equal to 5 times 10 to the minus 3 seconds, or it is equal to 5 milliseconds. All right. Okay, moving on. The value of the current after a time equal to a specific time. We are in the charging phase, so we're just going to be using these equations. So they're talking about current, so we're using I is equal to I max. Remember, the big I is just I max. 1 minus e to the power minus t over tau. Okay, so I is equal to I max 1 minus e to the power minus t over tau. Now to the value of the current after a time equal to one time constant from the instant supply is connected to IL. So what does it say here? It says equal to one time constant. What does that mean? Our time constant, we have found the value of it. So T is equal to 1 times tau, or in other words, it is equal to tau. So it is going to be equal to our time constant value, which was 5 milliseconds, which is 5 times 10 to the negative 3 seconds. All right. So when they say equal to one time constant, it is very easy. You have already found your time constant. If they say equal to two time constants or half a time constant, same exact concept will be applied. You're just going to multiply it by the value you found for your time constant. All right. And you found your T value. So now we just plug into our equation. So we found our I max earlier to be 19.17 times 1 minus e to the power of minus t, or minus tau over tau technically, لأن t is equal to tau. So if you notice, these two we're going to just cancel out each other without even having to plug in the value of time constant. All right, so keep that in mind. If you did not find your time constant at all for the circuit for whatever reason, ما عندكم time constant, but they give you time in terms of time constant, that is sufficient to cancel it out. All right, so in this case, when they say time is equal to time constant, we don't even care about the values. We do not require them at all. لأن we are taking it with respect to the time constant, which is a part of the equation as well. فمعناتها تقدرون تعوضون التime in terms of time constant and just plug it in. All right, so it is going to be equal to 19.17 into 1 minus e power minus 1, which is equal to 19.17 times 1 minus e power minus 1. It will give us 12.12 amperes. Again, this current cannot be larger than your I max. Okay, this is the maximum current. If you get a larger value than I max, معناته you have most probably done a mistake in your calculations. The last part is the expected time for the current to rise within 1% of the final value. What does this mean? This means, this is some theory that you guys need to know. This means it has basically reached the steady state. Okay? This is what it means. معناته the value is just entered the steady state. And this will occur after 5 time constants. Okay? This is just the rule. This is the القانون ماله. إنزين? So when you reach steady state, so part D, reach 1% of final implies that you are reaching the steady state. ما معناه steady state يعني خلاص وصلتوا المرحلة النهائية انه خلاص بيتم steady يعني ما بيتغير في شيء. الفاليو بيتم نفس ما هو طالما السيستم is not being touched or changed. إنزين؟ So when you reach 1% of the final value means you are reaching your steady state, which means your time is going to be equal to 5 tau when you want to reach this steady state value. All right, this is a very general rule and you're going to see this a lot later on in your future years as well. What did they want? What were they asking for? The expected time for the current to rise within that much. So they just want the time. The time is going to be equal to 5 times tau, which is 5 times 5 times 10 to the negative 3, which is equal to 25 times 10 to the negative 3, or 25 milliseconds. This is in seconds, this is in milliseconds. Another way you can think of this, if you don't memorize this equation over here, another way you can think of this is by plugging it into the time over here, or solving using this equation. When I is equal to I max. So, or this is reach 1% of final, meaning reaching your steady state value. Or you can say that I is going to be equal to I max. So when we plug it into the equation, we're going to have I max equal I max 1 minus e to the power of minus t over tau. To be a bit more accurate, it is not exactly I max. You want to reach 1% of the final, within 1%. Yani basically, I is going to be equal to 99% of I max. بما معنى. So you can say that this is actually going to be 0.99 times I max if you want to be a bit more accurate. All right? لأن you are reaching within 1% of the final. You are not reaching the exact final. باقي لكم 1% to reach the final. معناته you have completed 99% or you want 99% of the total current. All right? So if you notice here, IM and IM will cancel out each other anyways, and you will be left with 0.99 is equal to 1 minus E minus T over tau. معناته minus 0.01 is equal to, زين, if we take the 1 to the other side, it's going to be equal to minus E T over tau. The minus and minus will cancel. You will get 0.01 is equal to E minus T over tau. E minus T over tau. If you do the ln of 0.01, you're going to get minus 4.605 is equal to minus T over tau. If you notice, your tau was what? It was 5 times 10 minus 3. Again, the minuses will cancel. If you notice here, you are very close to the value of 5 times tau. All right, so before I even plug this in, this is your tau. Okay, this will be equal to 4.605 tau. Or in other words, if you round up, it is 5 tau. Okay, this is basically what it means. So you can either do it in this method, the long method. This is correct, by the way, 100% correct. There's nothing wrong with this. However, it is just simple to remember that when you're reaching within last 1%, your time is going to be 5 times tau, and just plug this in to your answer. Is this clear? Anyone has any questions about this so far? As you see, it is exactly the same as solving for your current, for your voltage. What am I saying? For your RC circuit, it's the same exact way of solving. Let me do one more question where it is being discharged, so you can see that it is going to be the exact same solving anyways. Then we will take a very short break عشان we can start with magnetism. All right. So a coil having an inductance of um, 8 henries. So our L is equal to 8 henries, and a resistance R, we're not given the value in ohms, is connected in series with a resistor of 3 ohms. So our other resistor, let's call it R2. Actually, this is the resistance of the inductance itself. All right, and I will talk about that in a bit. And with a resistor of 3 ohms, so our R is equal to 3 ohms, to 100 volts. So V is equal to 100 volts. All right, I will call this RL. All right, I will call this RL, which is the resistance of the inductance, because they said the inductance and a resistance of, yani this coil has a resistance. All right, then remember, an inductor is simply a piece of metal with coils around it, and they said that this coil has a resistance RL. All right, the time constant of the resistor of the circuit is 0.1 seconds. So our time constant is equal to 0.1 seconds. Okay, when the steady state is achieved, then when the steady state is achieved, the supply is replaced instantaneously by a short circuit. معناته initially we had a voltage supply, we had our inductor. By the way, an inductor is simply just the resistance of the wire plus the inductance itself. All right, so this is what I mean by RL, the resistance of the wire. يعني this is our small circuit that we have made it larger over here previously. اللي هو هني. This is the circuit. Okay, but this is basically in one box by itself. This is what is meant in this question. All right, so you have RL over here and L, and then you have another resistor in series connected, which is 3 ohms. All right, 3 ohms, and the voltage here is 100 volts. Okay, this is basically what they mean by this. So when we're looking at the time constant, we're not looking at this resistor anymore. We are looking at this resistor now, all right, to find the time constant. Because this is the resistor that is connected with the inductor directly, or that causes the inductance and causes the slowdown of charging. And we will see that in a bit. So let's first see what the question says. Find the resistance R, or in our case, we called it RL. So like I said earlier, for part A, our time constant is going to be L divided by RL, which is the RL that is connected over here inside this box. All right, the resistance of the wire. This is what we mean by a resistance, by the way. When we're talking here early on, when we're talking about the resistance here, we're talking about the resistance of the inductor. Same thing before for the capacitor, we are talking about the resistance of the capacitor. All right, this is what is meant by the components of the capacitor, yani. All right, so this is what is meant here. Again, we are talking about the component of the inductor itself. So to find our RL, all right, we don't look at our 3. For now, we don't look at our 3. We look at our RL plus our R, our total resistance in the circuit, since RL and R are connected in series. Okay, this is what we are going to be looking at. So again, I repeat, we're going to have a small resistance over here that is connected to the component of the inductor. And in this case, in this circuit, in this charging circuit, we have an additional resistor over here. So to find this RL, you're just going to find your R equivalent in this case, which is just in series, so you add them up. And the inductor is going to be divided by your R total over here to find your time constant. In this case, we are given time constant, we are given our inductor, but we are not given our RL. So this equation will become 0.1 is equal to L, which is 8, over RL, which we need to find, plus R, which is 3 ohms. Tamam? So again, I repeat, The idea here is you're looking at the total resistance of the circuit because this is your full charging circuit. So you can combine these two resistances and have them as one resistor. All right. So this will become 0.1 into RL plus 3 is equal to 8. So RL plus 3 is equal to 8 over 0.1. RL is equal to 8 over 0.1 plus 3, which is equal to 80 plus 3. Was it 0.1 seconds? Yes, okay. So it is going to be equal to 83 ohms. So your RL is 83 ohms. Okay, again, I repeat, the idea here is you're taking your total resistances because when you're charging, you have to consider all the resistors in your circuit. Yes, this is one part, it is one part, but it is a resistor at the end of the day in series with another resistor. So you can connect them in series. So you find your R equivalent, which is just simply adding them up. So this is for part A to find the resistance. Part B, they want us to find the current flowing through the circuit. All right. Oops, I made a mistake. Taking the 3 to the other side will be minus. Okay. So this will be minus 3 actually, and this will be 77 ohms. All right. Just an algebraic mistake. نشوف part B. Part B, they want the current flowing through the circuit 0.3 seconds after shorting the link has been placed in the circuit. معناته شو؟ الحين عندنا احنا الاندكتر with its resistor and it has been shorted with the other resistor. Okay? فصار shorting. فالحين احنا عندنا our RL, our inductor and our R. Okay? And all of them are connected together. The RL is connected to R in series, and they're both connected to L in parallel. All right. So if we find our equivalent over here, it is going to look like this. It's going to be, best so you guys can understand. This is your R equivalent or R total, which is equal to RL plus 3. What is our RL? 77 plus 3, so it's equal to 80. All right. So it's just R plus RL. That's it. Okay, 80 ohms. And this is your inductance L, which is 8 Henry. All right. So now when we are analyzing, we're going to be looking at our equivalent resistance or our total resistance. Tamam? So what does part B want us? The current flowing through the circuit. So first, the equation for current of decay. When we're looking at decay, where's the equation? These are the equations we are looking at because now we have a decay or we have discharging بما معناه. This is what decay basically means. So we're looking at the decay of current. It is simply I, small I is equal to large I, which is I max, e to the power of minus t over tau. All right. How do you find Im? Again, in this case now, we are looking at our equivalent resistor. So our Im is equal to initial voltage of the supply over our R total. All right. So it's going to be over R total. معناته I is equal to Im over R total or R equivalent. Let me just call it R total so that there's no confusion. All right. Our R total value over here. And we can just plug this into the equation. So it's E minus T over tau. Tamam? Again, it's all this question does. It's trying to trick you because they put two resistors in series. You will just add up these resistors as if it is one resistor and use the total equivalent as one component and continue solving as we have before. تمام؟ فالحين what is required? The current flowing through the circuit 0.3 seconds. So our time is given to be 0.3 seconds. I is going to be Im, or this isn't Im, this is V over RT. Im is equal to V over RT. So the voltage that we have, our initial voltage was 100 volts divided by R total, which is 80, E minus 0.3 over tau, which is 0.1. Put that into the calculator, and you will get I is equal to e power minus 3. So 0.0622 amperes. Tamam? Same thing again. We're going to be applying it for part C. The time taken for the current to fall to 35% of the final value. What does this mean? Our I final is equal to, so this is part C, it's equal to I max. Remember, from the curve, we are going to a steady state value. This is our steady state value. This is I max, which is our final value. So which is I max, which is V over R total, which we have found to be 100 over 80, which is 5 over 4, or 1.25 amperes. All right. So this is our I max. What does the question want us to do? To find the time when the current will fall to 35% of the final value. In other words, what do we have to do? I is going to be equal to 0.35 I max. That's all this means. Okay. Remember, this is actually discharging now. So the actual curve is going to look like this until it reaches 0. All right. This is our I max. It's our starting point, and it is discharging until it goes to 0. All right. So I is equal to 0.35 I max, and now we just plug in back into our equation of discharging over here. So we have 0.35 I max is equal to I max e to the power of minus t over tau. And we need to find our t value. So here I max will cancel out with each other. We don't even need the value of it. So 0.35 is equal to e to the power of minus t over tau. Using ln, we're going to have ln of 0.35 is equal to minus t over tau. بما معناه t is equal to minus tau ln 0.35, which is minus 0.1 into ln of 0.35. So our time is going to be 0.1 ln 0.35. That is going to be 0.105 seconds. Clear? Any questions? All right. Let's take a 5-minute break عشان we can start electromagnetism. This just comes with practice. The more you practice, the more you understand. Just before we take the break, again, you just have 2 sets of equations that you need to understand. You have, when you have a capacitor, you're going to have a time constant of C times R. When you using this time constant, you can find either capacitor or resistance. You're going to have your growth, or in other words, this is when you are charging. And then you're going to have, let me actually just make this clearer. So, summary over here. Charging capacitor is going to be this equation. Discharging capacitor, you're going to be using the other equation, which was over here. This equation, the decay بما معناه. All right. So discharging is decay and charging is growth. That's it. زين. Which is يعني بالمنطقة what makes sense. Growing, so it's charging. And this is going to be what you'll use for discharging. There's one less equation because VC is equal to VR in discharging, but in charging it isn't. So VC equal VR in this case. All right. Again, the exact same concept for inductors. So charging inductors, and you're going to have discharging of inductors. Okay, so for the charging of inductors, you're going to be using this set of equations over here. All right, and for the discharging, you're going to be using the equations that we just have used, which is over here. Tamam? That's pretty much it. So you're just going to apply these equations, just understand what the question wants from you, and know that in inductors, the time constant is L divided by R. And the charging is going to be the opposite of the discharging when it comes to capacitors, and that's pretty much it. All right. Discharging for both, it's exactly the same. Exactly the same. When you have a VC is going to be equal VR, here VL is going to be equal VR. And the equations as well, they're going to be the same because you are discharging. All right. But however, the charging, the growth is going to be different. The resistors are going to be growing, but the voltage is going to be, the induced voltage, I should say, will be decaying. In a capacitor, it's the opposite. The capacitor voltage is growing and the resistor voltage is decaying. Part C, I will explain it one more time. The question says, the time taken for the current to fall 35% of the final value. What is the final value of, in the case of an inductor? The final value is basically I max, right? That is what your final value is, which is given to you in your equation here. Your I here. This I is equal to I max or equal to I final. All right. So when you're trying to reach 35% of the final value, the time taken for the current to fall to 35% of the final value, معناتها you want 35% of this I final. All right. So basically, in other words, we are saying that I is equal to 35% of I max. So this is equal to 35% of I max. Remember, percent just basically means divide by 100. زين معناته we want to fall to 35% of يعني IMAX, which is going to be lower than this. زين so it's not going to be here, it's going to be somewhere over here of IMAX, right? This is our IMAX, this is 35% over here. زين this is 100% basically. Our IMAX is 100%. يعني IMAX equal IMAX, which is our I final value. Okay? That is basically how it is for part C. Let us take a 5-minute break. We'll be back at 5:20, and we will start, inshallah, with electromagnetism. All right. Okay, let us continue. All right. Here, try to focus up in the very beginning. And I will go through all the equations from the very beginning عشان you guys know the equations that will be given to you guys in the exam from the formula sheet, what they mean and how to use them. I'm not going to go through the theory of each equation, but I will be going through some problems to show you how the application of all the equations are. I will be talking a little about theory in the beginning بس عشان يكون عندكم فكرة on what we're talking about. إنزين. So now we are talking about electromagnetism. شو يعني electromagnetism؟ معناته creating an electromagnetic field through the use of electricity. Okay. Before even going into that, what is a magnet? تعرفون شو magnet طبعا. زين. عندكم a magnet which has two sides. It has something, a positive side here and a negative side over here, which I'm pretty sure all of you already know and have seen a lot. زين. So this positive side over here and this negative side over here, the way the theory of it works is simply that there is a field that this creates in this shape. So there's going to be a field that goes from the positive to the negative in this direction. This is also known as magnetic flux, right? This is known as magnetic flux, all right? And this is what it represents it. So magnetic flux, which is your which is given in the unit known as WB or Weber. All right, this is the unit of magnetic flux. So this is how it usually goes, and then some will go outside over here, and at the same thing from the bottom, it is going from positive to negative, similar to electric circuits or the conventional current. You can say direction, it's going from positive to negative. So here it will be going into negative, and there it will be going out of the positive. And this is known as the magnetic flux. This is describing the magnetic field around it. But what is the magnetic field around it? You cannot just say these lines are the magnetic flux. You have to, because these are imaginary lines, all right? The actual thing is when you take a specific area, and for example here, a specific area, the magnetic field in that location or in that area is going to be equal to, so the magnetic field given by B is going to be equal to the magnetic flux over area. All right, that's simply it. This is your first equation. All right, B is your magnetic field, or sometimes it is also known as flux density. Flux density. Or your magnetic field. زين ليش flux density? Because it shows how much flux is in a specific location. نفس density. Density is talking about how much mass is in a specific volume, and here you're talking about how much flux is in a specific area, and the unit is in Tesla or T. Right? This is the unit of your magnetic field. This is your area in meters squared, and this is your flux that we have just looked at, magnetic flux in Weber, which is WB. So this is your very first equation, and this is all of this is basically based on this theory. Then you're going to have something called, you're going to have an equation like this, which is B is mu times H. So B, we already know what it is. Mu is known as our absolute permittivity, and we will talk about that in a little bit, right? And its unit is going to be henries per meter. And then we have our H, which is known as our magnetizing force. And the units of this is in amperes per meter. This is also sometimes known as magnetic strength. زين يعني the strength of your magnet بما معنى. So this depends on your absolute permittivity. What is absolute permittivity? If you remember last time when we were talking about capacitors, we had the same exact idea where we had mu 0 times mu r. This is our relative permittivity. Again, this is absolute permittivity for magnets, right? For magnetism. Same thing here. This is relative permittivity for magnetism. and this is your free space permittivity. يعني بما معناته vacuum permittivity for magnetism. زين. And this is your absolute permittivity. It's just the same equation. So this permittivity of free space is also a constant value of 4 pi times 10 to the negative 7 Henry per meter. And relative permittivity is relative value, so it doesn't have any unit. Again, you don't need to know too much theory about this, but this is just how much the material allows allows the magnetic field to be forced or to be available based on this on the type of material. So you're going to have a specific you have strong magnets and weak magnets. What does it depend on? On this constant. This is just a constant or a property of that material, similar to the dielectric in capacitors. And that will determine how much magnetic force or how much magnetic strength that material has. That's why you will be able to find how much the magnetic field is depending on these two values. All right. Very simple. You just need to, this equation is given. You just need to know what these values mean. The next thing we have is something known as our magnetomotive force. This is sometimes written as MMF, or sometimes it's given as FM. And this is simply equal to N times I, where N is your number of turns or number of conductors, and I is your current in amperes. Insane. So obviously, since number of turns is a constant, this is also going to be in amperes. All right. Magnetomotive force is just the force, basically, depending on how many turns you have around a specific object. Remember when I said that this is basically creating a magnetic induction. So the magnetomotive force is how much force is available due to how many number of turns times the current that is flowing through this. That's all it is. You don't need to know too much about theory. All you need to know is the value of it is in amperes, and you can use this equation to find its value. All right. Remember our H as well, our magnetizing force. So our H is also equal to Ni over L, where N and I is similar to here, the number of turns and your current, and L is simply your mean length of flow path. شو يعني هالشيء mean length of flow path؟ يعني if we're looking at this example over here, it basically means where does the wiring start from, let's say, this point over here. Let's make it down. So it's from here all the way to the end, let's say over here. This is where your wiring is starting until here. This is your mean length. زين بما معناه where the coil is starting until where the coil is ending. This is the length. You can use that with N times I, which is basically, in other words, Fm. So you can say this is also equal to Fm over L, right? Yani it's the same thing. Where L is your just the mean length of this to find your strength, or in other words, your the magnetizing force. All right. This is basically it. You're already given this equation. No need to memorize anything, but you need to know how to relate it. So you know that Fm is equal to Ni. معناته إذا معطينكم Fm, you should be able to find H as long as you have your L. You don't need the number of turns or current, and vice versa. You should be able to find Fm if you are given H and L, because you know that H is equal to Ni over L, and you know that Fm is equal to Ni. This is how you should be able to use your equations. The next equation we have is our S. This is known as our reluctance. All right. S is equal to 1 over mu 0 mu r A. All right. You know what your mu 0 is. You know what your mu r is. You know what A is. It's just the area. This is not given in the equation sheet, but this is also equal to Fm over your flux, right? Your Fm being your magnetomotive force, and your flux being the your flux being your magnetic flux at the very beginning that we have seen in Weber. And this reluctance is usually given in Henry minus 1 or in ampere per Weber as a unit. Okay. When we're talking about reluctance, what is exactly reluctance? Reluctance is just simply the resistance force. All right. Reluctance is basically the resistive force to magnetism. يعني هني this wire is going to cause electromagnetism, or it's going to cause a magnetic field inside. However, there is going to be some resistive force between the electrical part towards the magnetic part, depending on the material, depending on all of that. That's why your material properties are a part of this equation. So reluctance is just basically think of it as magnetic resistance. زين؟ يعني it's your friction of electricity to magnets. يعني think of it this way. إذا قاعدين نفكر احنا في ماي زين water flowing. When water is flowing it becomes slower because of the pipe wall. صح؟ يوم تحطون انتم ماي في البايب, pipe wall, it has friction which slows down the water. Same idea. Or if you're talking about current, when current is flowing through a wire, in real life you have resistance in the wire, so it is reducing the current. Same exact concept here for reluctance. When you have a magnetic field or a magnetic force, you're going to have some resistance to that magnetic force due to the properties of the materials all around it, and this is known as your reluctance. All right. And this is the equation you have. Remember, you can again combine a lot of equations together. If you know that this is Fm over theta in your formula sheet, you are only given 1 over mu 0 mu r a. How did we even reach this mu 0 mu r a? So the actual equation of this is Fm over flux. We know that Fm previously is Ni over flux. And previously we knew that flux is related to B and A. If we rearrange the equation, it is going to be B times A. So if we plug this back in over here, we're going to have Ni over BA. All right. And again, Ni, what is this? Ni is simply H times L. If we rearrange this equation, H times L is equal to Ni. All right. So we can say that this is H L over B A. And then the reason I'm showing you all of this is because everything is basically related to one another. فمعناتها there is a chance they will give you some properties where you do not have a direct way to substitute in equations. Maybe, I'm not sure. But you need to know that everything is related to each other and we are just plugging in values. If we rearrange this again, this is just simply L. If we take H to the bottom, this is going to be B over H. Then remember, this is the same times the area. All right. And what is B over H? And B over H is simply when سوينا relation over here. B is equal to mu times H. And what is mu? Mu is mu 0 mu R. فمعناتها B divided by H, and if we rearrange this equation, mu is equal to B over H. Or in other words, mu 0 mu R is equal to B over H. When you plug this back into this equation, and here for BH, you're going to have L over mu 0 mu R A. And this is how you got the final equation that I showed you early on. L over mu 0 mu R A. You see, so they're all related to each other. So make sure you understand what the value of each equation is. Remember, Fm is magnetomotive force. Flux is just flux, which is given as phi. N is number of turns. I is current. H is your it's your magnetic force. B is your field, your magnetic field. A is just area. Mu 0 and mu r is your permittivities. All right, mu 0 being a constant value, which is 4 pi times 10 to the negative 7, your free space permittivity, and mu r is just relative permittivity. So this obviously will come with practice, شوية memorization as well. And this is your basic electromagnetic or magnetic in general equations. But moving on, we're going to talk about induction as well. Induction, we also have some equations that you guys will need to know about. Induction is simply just the creation of electrical fields or magnetic fields due to electricity. And then this is what induction is. So if you look at your equation, the equation sheet or the formula sheet, you're going to have the first one, which is force, is equal to, this is actually still magnetic, B I L sine theta. What does this mean? this is the force that you have in newtons. It is going to be equal to your magnetic field in teslas. I is current, which is obvious. L is your length of wire, الطول مال الواير اللي عندكم إياه. And this is your angle between the field and wire. All right? The field and wire. What does all of this mean? And this is obviously in degrees. شنو معناتها كل هالأشياء؟ الفورce, when we're talking about force in this case, we're talking about when we have a magnetic field in Zain and we have current going through it. For example, let's say we have two magnets over here. All right? Two magnets over here. This is the south side or the negative side in Zain. So it's south or negative. No, let me not put N, عشان you don't get confused. This is south or negative. And this is also, this is your north, not your south. This is going to be your north. Oops, let me do it in red. So this is your north, or it's your positive side. So you're going to be creating a field in between them going from plus to minus. All right, you're creating a magnetic field. We're just talking about magnets, صح? So there's a force of attraction between this and this. But let's say these are fixed يعني in these positions. So there is a magnetic field, but they are not moving themselves. تمام? And then let's say, let me rotate this a bit عشان you see it a bit more in 3D. Let's say we put a two coil wires in the middle of this field. زين? Or يعني one coil or one wire in the middle of this field. And this is just a wire with current passing through it. So you can see it a bit more clearly. And then it will look something like this. All right. So it's basically going through these two, going through this field over here. And then, so when this wire is going through this field, you're going to have current flowing through the wire. You have current going through this wire. This basically will cause a force to occur over here in a specific direction, depending on the wire and all of that. And this is the force that we are talking about over here. The magnetic field is this B over here, depending on the values of your flux and all of that. Your L is the length of this wire over here that we have from here to here. This is your length. And your theta angle is basically the angle of this with your with the field, with the magnetic field that you have. So let's say, for example, this is not exactly a straight line. Let's say that there's a specific angle theta over here. And then this is what is meant by this force. The force that is being caused by this magnetic field when there's electricity going through it, and it depends on the length of the wire that is through it as well. All right. So this is the force on the current. Yani you can think of this as the force on current in this carrying wire, in the wire here where the current is flowing through it. The force of the magnetic field on this current that is moving in this wire. لأن it will either increase the force or decrease it. يعني basically make it move faster or slower. زين? يعني it will induce an electrical current based on the magnetic field. This is what it means. All right? No need to know too much about the theory of this. What you need to know is something called the left hand rule, and this is used for the direction of everything. So like I said, we have the vector things, the things that have direction is force, magnetic field, and current over here, صح? So current can either be flowing backwards or forwards. Magnetic could be from right to left or left to right. In this case, we know it's from right to left. And then we have our force. What is the direction of the force? So how do you use the left hand rule? The left hand rule basically is if you have your thumb, and they have your finger, and they have your middle finger over here, and then you have your other fingers over here. يعني اعذروني على الدروينج التعبان بس you're using your left hand. This is your left hand. زين The left-hand rule says that this will be the direction of your force. Yani if it's pointing upwards, this is the direction of force. That way will be the direction of your magnetic field, which is B. And this is the direction of current. تمام? I. This is how you use your left hand to know direction. So basically, you're as if you're shooting a gun with your first, يعني with your thumb and your index finger. You're shooting a gun. وبعدين the middle finger يكون perpendicular to both. All right. So that will be your direction of using your left hand, not your right hand. That will be the direction of your force, your magnetic field, and your current when you are using the equation over here. تمام? So all you have to do is just plug in values, and we'll see that in a bit. What other equations do we have? Yes, so obviously here theta, if this was perpendicular, معناته if perpendicular, that means 90 degrees. معناته sine theta is equal to 1. معناته you don't even need the sine theta part. It is simply just B times I times L. Okay? Moving on to our electromagnetism. Induction, I should say, to be more specific. When we're talking about induction, we're going to see something known as our induced EMF, which is our induced electromotive force, which is simply just voltage. And this is usually given by the letter E. This is basically the voltage due to the induction that is occurring depending on how it is happening. So you're going to have three main equations for this. The first one is, we're now talking about self-induction. We're not talking about mutual. Mutual will leave to the end. All right. So for self-induction, we're going to have E is equal to the negative N d theta, or d phi, I should say, by dt. What does this mean? Remember, all this means is change. When you see differentiation, معناته change of theta is or phi is flux in Weber by the change of time in seconds. Then d theta by dt. معناته you're going to put change of flux divided by change of time, and n is simply number of turns. Okay? This is, and E is your EMF, your induced EMF in volts. Another equation you will see is in terms of an inductor. But for the inductor, it is not going to be change of flux, it's going to be the change of current by change of time. So again, this is just change of current in amperes over change of time in seconds. And this is just your inductance, the value of your inductance in henries. Just like the inductor value from before. Another thing, another formula you could say, you could find your EMF with is when you have a magnetic field given, B times L times V, and I'm not going to put capital V, I'm actually going to put a V like this, times sine theta. Why am I putting V like this? This is velocity. All right. What is this talking about? I'll explain in a second. Velocity in meters per second. This is the angle again, as we've seen before. This is the length of conductor in meters. And this we have already seen, our magnetic field in Tesla. And this is our EMF, voltage or induced EMF. Okay? They are all induced EMFs. Induced معناتها created بما معنى. All right? Which is voltage. And this is angle between conductor and magnetic field. So what does this exactly mean? Yani, what is this equation explain? What is this equation even talking about? This equation is basically describing when you have a conductor, yani, when you have two um, magnets, let's say, something like this, one up and one is down. All right, I'm gonna draw it a bit lower just so I can explain the concept a bit more. So one of them is gonna be positive or north, which is positive, and one which is going to be negative, which is south or negative. And you're gonna be passing a conductor between it at a specific velocity, yani you are moving this conductor at a specific velocity. All right, so this is moving at a specific velocity v, and it has a specific length. All right, this is our L, the length of our conductor. All right, yani it's a piece of metal that can conduct, and it is being moved between these positive and negative fields. So obviously the positive and negative, they're going to be causing a field around from positive to negative like this. This is your magnetic field B, and that's it. And this is all your values over here. So this will have a specific voltage depending on your magnetic field B, your L, which is the length of this conductor between the two magnets, your velocity, which is the velocity of this conductor going through these two plates, and your theta, which is the angle of this conductor with your magnetic field. Sometimes it could be going at an angle. In this case, it's going perpendicular, معناتها 90 degrees, but sometimes it could be going at an angle depending on the question. And this is how you can find your induced EMF in this case. Let's see other equations that we might have. Yeah, the equation sheet. Okay, and then is there anything else here? لا. Okay. Now, what about this L over here, the inductance? How can we find, for self-inductance, how can we find L? L is equal to N. This is, again, remember, no memorization, only understanding. This is all given in your formula sheet. This is your flux, magnetic flux, which you already know. And this is your number of turns. And this is your current. All right? Very simple. Remember, this has to be in Weber, not milliweber, and this has to be in amperes, not milliamperes. Then, or it is also equal to N squared over S, which is reluctance. If you remember, we already saw this before. Reluctance, which is in Henry minus 1. Okay? And this is just the number of turns squared. Okay? So this is another equation that you will use to find your inductance or self-inductance depending on and the number of turns and the magnetic flux and all of that. All right. And it's all of this, by the way, it's talking about situations like these where you have a positive and a negative magnet, and between them there is a coil or there is something moving or whatever it is. Okay. The last thing we're going to talk about is mutual inductance. Mutual inductance, معناتها you have two things that are getting inducted. يعني something is inducting something else. All right. So, for example, the first equation we have is M is known as mutual inductance. يعني basically this will replace your L, all right? Mutual inductance is known as M, which is in Henry, H, all right? The same unit, nothing has changed. Same exact unit, okay? Mutual inductance is basically, like I said, when it's happening between two coils, and this usually happens in transformers. يعني مثلا إذا عندكم Transformers, not the movie, Transformers اللي عندنا في الشوارع بس عشان تتأكدون. Okay, so if you have two coils over here, one over here مثلا, and one over here which is much more packedly tied, this is what is meant by mutual inductance. Then you have the same material holding both. So this material is going to have current going through it, obviously. Current going through it, or not current, I should say, a magnetic field that is going through it, and it is being transferred to the other coil. And this is what mutual inductance is. All right. So you have two different sets of coils. What is the equation for it? We have two equations. The first one is M is going to be equal to N1 N2 over S, which is your reluctance value. Okay, this is the first value that you're going to be using. S meaning the reluctance value. N1 is the number of turns on first coil, so turns on first coil, for example, the blue coil, and this is the number of turns on second coil. Okay, and S is your reluctance, as we have seen before. The last equation that you guys will be given in your exam is your EMF in a mutual inductance is going to be equal to minus M di by dt. But to be more specific, this is E2, so the electromotive force on the second coil. So this is EMF on second coil is equal to your mutual negative of the mutual inductance times the change of current 1. So this is the current or change in current of first coil, okay, in amperes. And this is just change of time, as we have seen before. All right. And this M is your mutual inductance. Tamam. I know I talked too much, and this is just, I didn't even go into theory that much. I just wanted you guys to understand how to use all these equations. Because now, if you solve any problem, you're just going to notice that all you have to do is just plug in values. That's it. So if we go to inductance, let's choose a random one. Then at the beginning one, it is very direct, but just to see, I'll just solve the very first question عشان تفهمون how it will look like. So here it says a magnetic pole face has a rectangular section having dimensions 94 millimeter by 127 millimeter. 94 millimeter by 127 millimeter. What does this mean? This basically means that you have 94 times 10 to the minus 3 or 0.094 meters by 0.127 meters. And your area is going to be the multiplication of both 0.094 times 0.127, which is 0.011938 meters squared. We have our area. If the total flux energy emerging from the pole is 225 micro Weber, معناته your flux is equal to 225 micro Weber. Micro Weber, what does that mean? 225 times 10 to the negative 6 Weber. B will be, so what is our B? B is equal to flux over area, which is given in our equation. So it is equal to 225 times 10 minus 6 divided by our area, which is 0.011938. Find the value, and that's it. Most equations are going to be like this, simple. Most of the questions are just straightforward like this. Let me look for a question which has some other additional concept, for example. Okay, actually, the second one is good. Here, this equation says the maximum working flux density. Remember, flux density is B. Then flux density is your B. Of a lifting electromagnetic is 0.51 Tesla, not ton. This is Tesla, the unit of flux density or your magnetic field. All right, they have the same unit. And the effective area of a pole face is circular and cross-section. Find the total magnetic flux produced. If the total magnetic flux produced, يعني flux is 106 milli Weber. يعني 106 times 10 minus 3 Weber. All right? Determine the radius of the pole face. Very simple. They said the area is equal to a circular cross section. شو يعني circular؟ معناته the area is pi r squared. Plug into your equation B equal this over area. معناته area is going to be equal to flux over B, Once you find the value of area, you're going to solve for R from this equation. So it's going to be R is equal to A over pi under the square root, and you find your radius. Tamam? I'm solving these very quickly because I want to go through as many concepts as I can. And that's it. So let's look at the next one. The idea is to understand what the question wants. فهني it says a magnetizing force. What does a magnetizing force معناته شنو؟ Oops. Well, a magnetizing force معناته H. This is what a magnetizing force is. So H is equal to 3471 ampere Tesla per meter. Is applied to a circular magnetic circuit of a mean diameter. معناته we have a diameter D is equal 68 centimeters, or in other words 0.68 meters. تمام? So by passing the current through a coil wound on the circuit, if the coil is uniformly wound around the circuit and has 549 turns, so our N is 549 turns. Okay, the current in the coil will be, so we need to find I. What is I? So which equation can we use? We can use the equation that we have formulated early on, which is H, and this is also given in your formula sheet, is Ni over L. But we do not have the value of L. How can we find the value of L from this question over here? We are talking about a circular. What was L? If you remember, H. What was L? L is the mean length of the flow path. بما معناه mean length of the flow path means it is equal to your circumference. This is what it is. It is equal to your circumference. معناته, like I said, it is going to be the circumference that is going around over here. So L is going to be equal to the circumference of a circle is what? Pi times D, or 2 pi R. So this is the trick over here. It is knowing that this is going to be equal to Ni over pi D. Tamam? This is what it is. Now we have D, we have H, we have N. We need to solve for I. If we rearrange this equation, we're going to get that I is equal to H times pi times D divided by our N. All right, we're just rearranging this equation, and we have the value for each one, and we will plug in and solve. Tamam? Like I said, there are tricks, and these are tricks that you have seen already from before. I think from the first session, if I'm not mistaken, we had some coil wounds and all of that. Just read and understand what they mean by that. As long as you understand the concepts early on, you're going to be fine. Okay? Let's look at the next one very quickly. ما ظني بنخلص, بس I'm just going to try to go through them as fast as I can عشان just to explain the concept. A current of 7 ampere is passed through a 736 turn coil wound. So what does this mean? 7 ampere معناتها I equal 7 ampere. We have current. 736 turns معناتها N is equal 736. Circular magnetic circuit of radius. So we have a circular and we have a radius. معناته our radius R is equal to 120 millimeters, or 0.12 meters. تمام? The magnetomotive force is, so we need to find MMF or FM, which is N times I. All right? We need to find N times I. It's very straightforward, very simple. How do you do this? You just multiply your N over here, your 736, by 7, and that's it. And you find your FM. But the idea is knowing, yani they're not going to give you the trick over here saying MMF. You guys need to know it by yourself. Okay? Let's add an extra question. Let's say find H, or your magnetic your magnetizing force. How are you going to find it? H is equal to Ni over L, or in other words, Fm that we have just found over L. What is going to be the value of L? L again is your average circumference. معناته L is equal to pi d, or in this case you are given radius, so it's 2 pi r. معناته it's equal to Fm over 2 pi r. So we're just going to plug in the value 7367 times 7 over 2 pi times the radius r. تمام? The formulas that I am using are all given, but you guys need to know how to use them and when to use them. يعني Fm equal Ni, all the formulas that I have explained early on, already given to you in your questions or in your exam. تمام? Let's look at the next one very quickly. Tara, there are too many questions. There's no way I'll be able to solve all of them, but I want to go through as many as I can. A current of 1.8 amperes, and this is I, passed through a 358 turn, N is equal 358, on a circular of radius equal 51 mm, or in other words, 0.051 meters. The magnetic field strength will be. شو معناته magnetic field strength? What does magnetic field strength represent? Magnetic field strength is H, and you will solve the same. So see, the idea here, you need to know what they want from you. Magnetic field strength, or the previous one they said, magnetizing force, they're the same thing. It is your H value. Then you will solve as you have solved before. It is Ni over R, which is, so it's over L, which is Ni over 2 pi R. And you will solve. Tamam? Let's go to the next one. Is producing piece of gas, magnetizing force. Find the relative. And they want you to find relative permittivity in this question. How do you find relative permittivity? Again, you use what you're given. So you're given B is 1.3, flux density is B, 1.3 Tesla, produced in a piece of cast steel by a magnetizing force. Magnetizing force means H is 1400. Find the relative permeability. So the equation that we have is absolute permittivity. This is the equation given to us in our formula sheet. So here you're going to find that U or mu is equal to B over H. Tamam. But this is absolute permittivity. They want us to find mu R. How do we do that? To find mu R, we know that mu is equal to mu 0 times mu R. And mu 0 is a constant that they will give you, which is 4 pi times 10 to the minus 7. So mu R is going to be equal to mu over mu 0. So basically you have to use two equations to find your final answer. Remember that this mu is not your relative permittivity. That's what I mean by read the question properly. Relative permeability is your mu R. So معناته you have to use this equation, and then once you find your mu, you will have to use this equation to substitute mu and find your mu R, which is mu over mu 0. All right. Let's see. Let us move on to something with reluctance, for example. Okay, I think this question over here. The magnetizing force, relative permittivity. Okay, here. So let's look at this question. This question says a piece of metal شنو ما ادري. زين, a piece of metal has a length of 140 millimeter cross sectional area. Length is equal 140 mm, or in other words, it is 0.14 meters. And the cross sectional area A is 1,800 millimeters squared. If you do the conversion here, remember, you're going to have to divide by or multiply by 10 to the power of minus 3 squared, or minus 6. معناته you're going to get 1.8 times 10 to the minus 3 meters squared. All right. So again, to go from millimeters squared to meters squared, it's times 10 minus 6. And I've shown you how to get this value last time. Okay. And has a relative permeability of mu R equal 3,600. Given mu 0 equal this much, 4 pi times 10 negative 7. Mu 0 will always be given. The reluctance offered by the metal. What is reluctance? S is equal to L over mu R mu 0 A. معناتها you're just going to be plugging in all these values in and you will find your reluctance. The absolute permeability mu is simply mu 0 times mu R, which you have over here, and you just plug it in. This turned out to be a very easy question, unfortunately. Let's look at the next one. I think this is the one with the ring. Yes, okay. So here in this question, a mild steel ring has a radius R of 80 millimeters, which is 0.08 meters, all right? And the cross-sectional area of 200 millimeters squared. So area is 200 millimeters squared, which is equal to 200 times 10 negative 6 meters squared. All right. So if you want to memorize this conversion, you can. It is just 10 times minus 6. A current I flows of 0.5 ampere in a coil wound uniformly around the ring, and the flux produced is, so we're given flux as well, 0.1 milliweber, or in other words, 0.1 times 10 to the minus 3 Weber. Make sure as soon as you note down your given, convert it as soon as you do. If the relative permeability is given to be 170 and mu 0 is given to be 4 pi times 10 to the minus 7. Find the reluctance. So now we do not have the length anymore. We are given the radius. Remember, reluctance is length over mu r, which we have, mu 0, which we have, area, which we have, all right? But we do not have the length. However, how do we find the length? Same as we did before. L, the length is the average or the mean length. So how do you find it? It is just 2 pi r over mu r mu 0 a, okay? This is what your L is, because they said in a coil wound uniformly around the ring, meaning that L is a uniform, يعني, the average is going to be equal to the circumference of the wound itself. تمام? This is for part A. Part B, it says find the number of turns on the coil. This is the one I want you to see. So we need to find N. How do we find N? We have a lot of equations that we can use. So now we have already found our S. How can we relate S with N? If you notice, we cannot use this equation, obviously, but there are a lot of different equations that we can use depending on the given values that we have. Remember this thing. Remember that S is also equal to Fm over flux. This is not given to you in your formula sheet. So it's equal to Fm over flux. We know that Fm from the formula sheet is Ni, and that's it, and over flux. All right. And we know that we have N over here now. So we know, so we can say that S is equal to Ni over flux. We have a value of flux, we have the value of current, we found our value of S, so now we can find the value of N. Okay, this is how you will be able to solve in the exam. This is what most probably you'll be doing. You'll be relating equations to each other. So remember that S is equal to, this is very important, reluctance is Fm, which is your magnetomotive force, over your flux. All right. So if you rearrange this equation, it's going to be S phi over I. Again, this equation is not given to you guys in the exam. There's a lot of other questions as well. I want to go through them all, but I really do not have the time. I would recommend that you guys practice. Really, the questions are very easy. There aren't anything difficult. I haven't talked about this graph, but let me talk about it for 1 second really quickly. So what does this graph represent? This graph gives you your B value on the left, and it gives you your H value at the bottom. So you can find the value of your mu, or sorry, you can find the value of your B or your H depending on the type of material you have. So let's say you have cast steel, which is the first line over here, this line. This line over here that is going all the way down here. This is the line of cast steel, right? This green line, this green highlighted line, up. This is cast steel. and they tell you that B is equal to 1.2 Tesla, for example. Then you can find your H from the graph. How? You're going to go to 1.2 Tesla over here, and you are going to go to the line itself. And then 1.2 Tesla. And you're going to draw a line from here all the way to the bottom, and you're going to see that it is roughly 1,500 magnetic field strength in ampere per meter. Okay? This is how you use this graph. It's very easy, very simple. It depends on the material given. So if you're given cast steel, for example, you'll go to the line of cast steel. If they give you B, you're going to use B. Or if they give you H, you're going to do the opposite. You're going to go to your H value. You're going to draw a line to the material, and then you're going to look at your B value. Okay? Very simple, very straightforward, just using this curve. All the other ones is just plugging in equations. I'm trying to look for one that isn't. Yep, they're all just plugging in equations. Just so you look at one of the inducting ones, inductance, يعني, let's look at this one. So when we're talking about inductance here, a silicon iron ring is wound with 600 turns. N is equal to 600. The ring having a mean diameter, so D is equal to 140 millimeters or 0.14 meters. A cross-sectional area, A, is equal to 200 millimeters squared or 200 times 10 to the negative 6 meters squared. Carries a current I equal 0.1 ampere. The relative permittivity, P mu R, is 2900. Mu 0 is 4 pi times 10 to the negative 7. The reluctance. So the reluctance is very straightforward. Reluctance is S is equal to L over mu 0 mu R A, and this is given to you in your formula sheet. And in this case, we don't have length, but we have the mean diameter, so it is going to be pi D over يعني the circumference over mu 0 mu R A, and you find your reluctance. The self-inductance of the coil. What does self-inductance mean? Self-inductance means L, your value for L. So if you go to your formula sheet for L, you're going to have two equations, all right? You're going to have L is equal to N squared over S, and you have one that is, نسيت تصدقون. I have explained it towards the end over here. This one, which is N flux over I. N flux over I. Okay? So how do you know which equation to use? Well, here we don't have flux. Flux is not given. Current is not, it is given actually, but we want to find, but we have the simpler one, which we have number of turns, N, and we have the what you call it, the reluctance اللي طلعناه من part 1. So we can simply just plug in the values for N squared, which is 600 squared, over S, which is the reluctance value that we found from here. And we have found our self-inductance. See, it is very straightforward. All you do is plug in values. The EMF induced in the coil if the current is reduced to 0 in 20 milliseconds. Okay? What does this mean? And then, what does this mean? So we need to find EMF induced. EMF induced, if you remember our equations, the one that we have for self-inductance was equal to negative L di by dt. All right? So here it says the current is reduced to 0. معناته the change of current, remember, change of current is current final minus current initial. That is what change in current is. Okay? Let me put this on the side. So change in current is simply the current final minus the current initial. So, in other words, excuse me. In other words, what was our initial current? It was 0.1. So we have this as 0.1. And what was the final current that we reached? It was reduced to 0. So it is 0. So 0 minus 0.1 is going to be, we have found our L value from the previous question. So it's minus L into 0 minus 0.1. divided by, so again, our L value, we already have it. Technically, we have calculated it from here, over the change of time. So the change of time is what? 20 milliseconds. So 20 milliseconds dt is from 0 to 20 يعني بما معنى. So it is 20 milliseconds, which is 20 times 10 to the negative 3 seconds. And you'll just put 20 times 10 to the minus 3 seconds. Calculate and you will find your value for E. And that's it. That's how simple it is. Okay? So, and your E, the value of it is going to be in volt. So you're just going to multiply L by this over this and the negative, don't forget. And that's it. And this equation is given to you. All the equations here are given to you already. Okay? This is for self-inductance. Let us just go through one, which is, let's do this one with mutual inductance. And then, for mutual inductance, the magnetic circuit shown below, the current in the primary coil, meaning the initial coil, or N1 you can call it, or NP. So I'm going to call it NP because in the graph it's given NP, or in the diagram, 1000 turns. Increases linearly from 2A to 7A. What does that mean, increasing linearly? Yani your I initial, this is for your primary now, right? We're talking about our primary. Okay? So IP1 or IP initial, let's call it IPI, is equal to 2 ampere, and IP final is equal to 7 ampere. And what is our change in time, dt? In how many seconds? It is equal to 250 milliseconds, or 0.25 seconds. Why do I write it in this way? So you guys understand that there was an increase linearly. معناته the change in current of primary is equal to 7, which is final, minus initial, just 2, not A. And it is 5 amperes. All right. So we have our change in current and we have our change in time. So we already have that for our EMF later on. An EMF of 15 volts is induced. So we know a 15 volt is induced where? In the secondary coil. معناته now we are looking at our secondary coil. Secondary EMF, or ES, meaning E secondary, is going to be equal to 15 volts. Then of 470 turns. So N secondary is 470 turns. Okay, which is left open circuited. The mutual inductance between the coils. So again, we have two equations for mutual inductance. The first one is M is equal to N1. Let me just find it 1 second. And N1, N2 over reluctance. So N1, N2 over reluctance. This is the first one that we have. N1, N2 over our reluctance S. Okay? This is the first one that we have. But here we don't have anything for reluctance, so we cannot find it based on reluctance. What is our second one? It is E2 is equal to minus M. Was it minus? I don't remember if it was minus or not, but I'll check now. DI1 over DT. Okay? So this was our second. I don't think there was a minus here. That was for normal inductance. Either way, this is your second equation for mutual. So you only have these two equations that you can use, either this one or this one. And then in the secondary, we do have, think of it as primary is our number 1 and secondary as our number 2. So we have E secondary, which is E2, we have it. So E2 is 15 volts is equal to M. And we need the change in the first one, the change of current in the first one, and we have it, which is 7 minus 2, which is 5. And the change of time is 0.25. And now you just find your value for M. And that's it. That's how you solve for finding M. You will find the value. So let me just do the calculation real quick. Times 0.25 divided by 5, 0.75 Henry. So our mutual inductance is Henry. the reluctance of the former. Now, how can we find the reluctance? Very simple. We can use the first equation. So for part B, this was part A. Part B, we can say M is equal to N1, N2 over S. معناته S is equal to N1, N2 over M. So what do we say? S is going to be N1 is the number of turns in the primary, which is 1,000, times the number of turns in the secondary, which was 470, divided by M, which we have already found to be 0.75. So it is equal to 100 times 470 divided by, or 1,000 times 470 divided by 0.75. You're going to get a large value of 62666. 1, 2, 3, yeah, 62666.7. And the unit of reluctance is either Henry inverse, yani you can write it as Henry inverse, or you can write it as ampere per Weber. Then this is the units of it. Henry inverse, why? Because look, it's just divided by Henry. M is in Henry, this is number of coils. All right, so it's just Henry inverse. Now part C, what does part C say? Part C says the self-inductance of the primary coil. We're talking about self-inductance right now. شو يعني self-inductance? معناتها we are going to be using our L equation. We do not have magnetic flux, so we cannot use the one using magnetic flux. We have to use the second L equation we have, which is N primary squared, because this is L primary, N primary squared over S. S is the same, because what are we having? We have the same material. Remember, S is S is the resistivity. Think of it that way. Resistivity to magnetism. So it depends on the material, and this is the same material for both. So your S value is the same for your secondary and your primary. So you'll have the same S value. معناته your LP is going to be NP squared, which is 1,000 squared, divided by the value of S, 62666.7. And you'll find your LP. And that's pretty much it. إنزين. I wish يعني I know I went a little bit too fast for this, okay?